Hey there, it's Jason Gorman from Codemanship with another video in our series on codecraft for Python programmers. In this video, we're going to be talking about the principles of simple design. This is a hierarchy of design principles, courtesy of our friend Kent Beck, that we apply to our code over and over again, allowing a design and architecture to emerge through the application of these straightforward design processes. Now, they're very, very simple, or they'll certainly sound simple, but they have some potentially quite complex implications, as we'll see. So, it's a hierarchy of design needs or design goals for our software, starting with the most important quality of any software design, which is that it's got to work. How do we know that it works? Because it passes the tests, provided, of course, that we can put faith in our tests. So if you refer back to our video on mutation testing in Python, that's one way of giving ourselves a good feel as to how much faith, how much store we should put in our test suites. So keep those tests running. Make sure that at every juncture the code works and it stays working after every change that we make. If it doesn't work, it doesn't matter how elegant or object-oriented or whatever our design is, it's the wrong design if it doesn't pass the test. So keep those tests passing. Provided that it works, the next thing that we worry about is how easy the code is to understand. As Kent puts it, does the code clearly communicate its intent? In other words, can we understand what the code is doing just by reading the code? So as much as possible, we want to make the code tell its own story. We estimate that developers spend between 50 to 80% of our time just reading our code, not just code that other people have written, but code that we wrote. So the easier it is we can make it to understand that code, the easier it's going to be to change that code safely. So make sure that it works, make sure the code clearly communicates its intent, and then we look for duplication of the code in the code. And the kind of acronym that a lot of people apply here is DRY, don't repeat yourself. The goal here really is to make sure that things are only happening in one place. From a maintainability point of view, duplication can hurt us because, for example, if we copy and paste a class and create multiple related classes rather than using inheritance or containment and delegation or something like that, then we end up multiplying the cost of changing the common logic in that duplicated code. So it can hurt us in that respect, but it's by no means the worst thing we can do in software. We might often choose, for example, to leave duplication in the code if it makes the code easier to understand. Remember, this is a hierarchy of design needs. So whether the code clearly communicates its intent is more important than whether or not it's free of duplication. But the other really interesting thing about duplication in code is, well, if you think about it, the opposite of duplication is reuse. So going back to my example of copying and pasting a class, if instead of doing that and creating duplicates of that code, instead what I did was make a reusable class that the other classes could use, so all the common stuff is contained in a reusable element, then we're essentially containing all the knowledge of how to do that piece of work in one single place, which means it's a single change. But we also end up introducing reusable elements into the design, abstractions like parameterized methods and reusable classes and so on. So by removing the duplication from our code, we begin to introduce the kinds of abstractions that we would expect to see in a reusable architecture, in a good architecture. So it often gives us hints about what the design really wants to be. It's a more scientific approach to introducing abstractions into our code, because if we're seeing multiple examples of something, we're more likely to choose the right abstraction. And that refers back to a previous video when I talked about duplication and the rule of three. So we don't necessarily jump in straight away when we see two examples of duplication. We might wait, on average, we wait to see three examples, so that we're less likely to pick the wrong abstraction when we remove that duplication. But we don't leave it too long so that we've ended up introducing many, many examples, because then that's going to be a big refactoring, and the bigger the refactoring, the less likely it is that we'll do it. So the sweet spot is around three examples. So we watch and we wait and we see those three examples of duplication. We look for the pattern in that, what's common to those three examples. And then we hopefully introduce the right abstraction. Certainly we introduce a better abstraction based on the evidence of the code that we've already written, rather than speculating about what we think that reusable element, that abstraction needs to be. That often doesn't work out so well. So we make sure that our code works. We make sure that it clearly communicates its intent, that you can understand what the code is doing just by reading the code. In other words, the code tells its own story, so we need to pick names very carefully, introduce names for pieces of code that maybe need explaining, and so on. And then we make sure that our code is free of duplication. In reality, we're going to make sure that it's low in duplication, because we may choose on occasions to leave that duplication in to make the code easier to understand. And of course, remembering the rule of 3, that we don't, if we've got 2 examples, it's not such a big deal. We might want to just leave that as it is. And we're more likely to pick the right abstraction, and duplication often leads us towards those useful abstractions, which is why some of the best frameworks are not designed up front by going, well, what do we think these users will need? They're kind of discovered by eliminating duplication from code, maybe from a single project or from multiple projects. A great example of that is unit testing frameworks, the X-unit pattern, as it's called, for unit testing frameworks. If you've ever written your own unit testing code from scratch without using, PyTest or something like that, you will often end up discovering the same abstractions that many other people have discovered when they write their own unit testing code. And those abstractions can be essentially put into their own framework, so that then that work doesn't have to be done over and over again. And those frameworks tend to be well designed because they're designed backwards from duplication, if you like, by removing duplication from code, from test code in this case. And finally, from which it gets its name, we want to make sure that the code we're writing is as simple as possible. As Kent puts it, it has as few parts, as few moving parts, if you like, as possible. Simpler is better. Simpler is easier to make work, and it's less likely to be broken, simply because there are less ways for it to be broken. So the simpler it is, the easier it is to understand, and the easier it is to get it working and to keep it working. And the acronym here that you may have heard is YAGNI, you ain't going to need it. So a lot of developers find this last one particularly hard, because we're often, for 2 reasons. One is we're often very solutions driven. So we're sort of trying to use things that we've learned. Maybe we're following a convention for architecture, for example. So I know many .NET developers who have kind of frameworks or templates, let's call them templates for solutions. And that template will often have multiple layers of their multi-layered architecture. So even though they've only got 1 or 2 classes, they've got like 4 or 5 different projects, often with no code in them at all, because that's the pattern that they followed. That's kind of the convention or the template that they followed. But we need to pull ourselves back from that and ask, do we really need those yet? Is that really the simplest thing we could have done? The other reason we find it hard is that, particularly with less experienced developers, we're often trying to prove ourselves, and we mistakenly believe that we prove ourselves by doing things that are very sophisticated, using all the design patterns, for example. So someone reads a book on design patterns, and then in their next project they have to use all of them, whether they're needed or not, whether they solve a problem or not. So you kind of have got to be hard on yourself here and question your motives when you include anything in the code base or in a project, as to, is this really needed? And kind of a good test here is I've used the word test. If you've got a good suite of tests that are driven directly from customer requirements, and when I talk about customers, as we'll see later, that doesn't necessarily mean business people, business customers or end users. There are other kinds of customers that we can get requirements from. If our tests are driven directly by their requirements, and our code is written specifically to pass those tests, then if we include code that's not needed, for example, we should be able to remove that code and all the tests will still pass. So we'll see an example of that in a minute. Okay, so those are the principles of simple design. And the idea is that on a highly iterative process like test-driven development, at every cycle we go through this and ask these questions. Make sure it works, first of all. Then read the code. If you're not sure if your code's easy to understand, get someone else to read it and see what they think. Look for duplication, look for opportunities to introduce abstractions, good abstractions, so don't necessarily jump in too early. Once you've removed duplication, it's important to stop and reread the code and ask yourself, is that still as easy to understand? And if the answer is no, maybe you should put it back the way it was. Maybe it's more important that it's easy to understand. And don't forget the rule of 3 here when it comes to duplication as well. Otherwise, you're going to end up introducing what we call leaky abstractions, the wrong abstractions, basically. And then finally, is this really the simplest thing that we could have done to pass the tests? And I know developers, for all sorts of reasons, find this hard. And you need to be tough on yourself here. I find that the more confidence you have, the more experience you gain, the easier it is to do the simple thing because you feel like you have less to prove. So the most experienced developers I know, the ones with decades and decades of experience, they're not afraid to do something very, very simple and basic. They're not worried about what other developers are thinking. And again, the acronym there is you ain't going to need it. So we'll see an example of that. So let's do an example. I've got some code here. It's our faithful Mars rover example that we've used in previous videos. And we take a look at this code. There's all sorts of things about this code that are jumping out at me already, but we'll come to them one at a time. But the most important thing we need to establish straight away is, does it work? So before we even think about any other aspect of design, let's just make sure that it works. All our tests are passing, and that's very, very good news. So we've ticked that first box. So at every juncture, before we start umming and ahhing about the design and whether it's the right modular design or whatever, we need to stop and we need to make sure that it's working. Okay, now we know that it's working, we can move on to thinking about how easy it is to understand this code. So remember, the goal here is to make it so the code clearly communicates its intent. And I'm not sure that this code does. I think, for example, there's a block of code here. What is this doing? What does this mean? What is this about? Well, one way we could make this easier to understand, make it self-documenting, would be to extract this code into its own method and use the name of that method to tell the story. So in actual fact, this block of code turns the rover to the right. So what I'm going to do is I'm going to, I've forgotten the shortcuts for PyCharm, it's been a while. We're going to extract, that's it, a method, Control-Alt-M is what I was looking for there. And we're going to use the name of the method to tell the story. So this thing turns it to the right. We'll use right here as a verb. Okay. And now that we've done that, now that we think that we've solved that problem, let's immediately make sure that it works. So we'll always come back to whether or not it works. That's the most important thing. Do not move too far away from that. And we can do a similar thing here with our left method as well. So what we're doing here is we're revealing some internal structure here. It's all one big method at the moment, pretty much. But we're beginning to discover some internal structure that helps to make the code more self-documenting, more self-describing. Did I just run the test? I get paranoid. Yes. And again, here, for example, this is turning the rover. This is moving the rover forward, I think. Let's just double check that's the case. The F for forward. Okay. And again, we immediately go back and make sure that we haven't broken it. Does it work? Always be testing, always be testing. And finally, this block of code here is moving the rover backwards in the opposite direction. So let's go back like that. So those are our instructions now documented as method names. So those are the ways in which we can begin to document what this code means. We've also got some opportunities here. For example, these could become constants with names that say this is what this means, this is what this particular instruction means, and so on and so forth. So we begin to refactor our code, introducing things with names or changing the names if they're misleading or not clear, to make the code essentially tell its own story. So if people want to understand what the code is, they can just read the code. That's what the code does. Okay, so we now got a bunch of little helper methods here. That's interesting. And as we're seeing, this internal structure is beginning to emerge as we refactor. And that's really what simple design is all about, is we apply these design principles in these little microcycles of TDD and refactoring. An internal design starts to emerge, and you'd be surprised just with these very simple principles about readability, about duplication, and about simplicity, about how sophisticated the kinds of designs that emerge can be over time. Okay, now, the other thing we need to think about now is duplication. So taking a look at this left method, these are all very, very similar. The only thing that's different is the actual data there. And I can probably make it more explicit if self-facing equals east. So we can now, that's a mistake I make over and over again. There we go. So I'm just making it a bit more explicit now that there are these all four are different examples of duplication here. So we're past the sort of threshold of the rule of three here. Let's just make sure that that little replacement there has worked. Okay, now what could we do to replace this? Well, having a little think about it, I'm kind of seeing, and now that I've got these four examples, I think I can see a pattern. And this is where the rule of three is very useful, because we want to sort of wait until we see the patterns. And the pattern looks, I suppose, a little bit like this. So if we imagine we have a compass, and we make that a list of north, west, south and east. Okay, like that. And we want to know where we currently are in the compass. So current equals index I'm not sure if this is how you do it. No, that's not how you do it. There's a Just give me a second while I Google this. It's been a while since I've done any. So just so that you know, these are live and edited, but I am just going to pause while I Google this. So it turns out that it was exactly what I was thinking there. I got a little confused. Apologies. So we know what index we are in that list. And all we're really doing with these, we don't need a semicolon, and all we're really doing with these is we're just moving forward to the next one in the list. So if we're facing north, we turn left to face west, and if we're facing west, we turn left to face south, and so on. The only difference, of course, being when we're facing east, but we'll get to that. So what we're doing really is kind of that, but for the last one, it's a little more complicated than that. If we're facing east, we're at the end of the list, and if we go over that end of the list, then we're going to end up array out of bounds, basically. So what we need to do is go back to 0, essentially. And one easy way of doing that would be to use the modulus of the length of the list. So in other words, if we end up with an index of 4, which is out of bounds, the 4 mod 4 is 0. So that takes us back to the beginning again. Okay, so we've discovered a little pattern there. Hopefully that will work. Let's get rid of the rest of this code. And that removes that duplication there. And that's looking good. I'm a little surprised, to be honest. I haven't done any Python in a while. And if you think about it, right is kind of the same thing. So I am going to speculate. I'm going to allow myself to speculate a little here. If we extract a method and call that method turn, and it turns in the direction of the compass, then we can reuse that. Let's just scroll down here. We can reuse that for turning right. It's just that the compass is in a different direction. So for this one, we're going north, east, south, west. In other words, clockwise. So turning left turns us anti-clockwise. Turning right turns us clockwise. Let's find out if that's worked. And again, there's an opportunity here. We remove this duplication, but is it easy to understand what's going on here? So what I'm going to do is I'm going to rename this to clockwise. No, anti-clockwise, sorry. Anti-clockwise. And I'm going to rename this getting a little obsessed with formatting there, and never a good look. And here we're going to introduce a variable, and we'll call that clockwise. So when we turn right, we turn clockwise. When we turn left, we turn anti-clockwise. And when we turn whichever direction. So I'm literally saying out loud what the code is doing, and then I'm choosing names that I think match like so that the code is telling its own story. So that's very, very important. Okay, and you can see that there is very similar kinds of duplication here. So again, though, there's probably a pattern here that could be reused. These look like vectors, 0, 0, -1, -1, 0, etc., etc. These look like vectors. So what we could do is maybe introduce some kind of list of vectors or a dictionary of vectors that we look up depending on which way we're facing, telling us which way to move. And then it's just a question of whether we add those numbers or subtract them for moving forwards and backwards. But I'm not going to do that now, just sort of point it out to you there. And again, we could hopefully make that self-documenting. So we've kept it working. Let's just check again. We've kept it working. We've made it hopefully easier to understand. It more clearly communicates what it's doing. We've removed some duplication and introduced some abstractions. In this case, we've introduced a bunch of methods and variables and other stuff with names. If you think of an abstraction in code as being a thing with a name, that's probably the easiest way to imagine them. And we've also removed some duplication, and hopefully that's made our code also, as we're doing that, a little easier to understand. So there's more work to be done, but I just want to move on finally to the last of the simple design principles, which is this really the simplest thing we could have done? And I want to draw your attention to these lines of code here. So there is some logging in here, and it is very, very common for developers to add logging to their code. But who is this logging for? My rule as a developer is I do not write code unless somebody asks for it. Now, we talked about customers. Customers don't have to just be business people or business users. Other kinds of customers, for example, could be the people supporting the application in operations. They might have requirements for the visibility of what's going on inside the application, inside the running application. So we might collect user stories from people in operations, or from people in the architecture team, or people in the security team, asking us to add things or to change things in our code in order to make the code to deal with the the illities, things like scalability and supportability and etc. etc. Now in this case, let's imagine that has not happened. And how do we know that it hasn't happened? Well, what happens if I cut that code out and rerun my tests? No tests are failing. I have no tests that require me to log. No tests that require me to log. Now, if someone in operations had come to me and said, we need this kind of information at runtime, we would have sat down and we would have agreed some tests that our software would have failed if that logging wasn't happening, if that visibility wasn't there. And so it's very, very important to be as test-driven as possible. And when I say test-driven, I really mean customer-driven. It's all coming from people's requirements, not just functional requirements from the business, but non-functional requirements from other stakeholders. And we write tests that fail because our software is not meeting those functional requirements, and then we do the simplest thing possible to make it meet those functional or non-functional requirements. And if all our tests are passing, we're able to remove that code, then arguably it was not needed. Now, I've seen many, many times when code is failing, when software is failing, that the thing that was actually failing was the logging code. Code is code, and all code can break, all code can go wrong. And the more code we add, the more likely it is that we're going to be introducing bugs, and also the more we're going to have to spend to maintain that code. So you need to be quite brutal here. You need to really, really question everything, the need for everything. And the ultimate arbiter is whether or not there are any customer tests that will fail if that's not in place, if that's not in the software. So there you go. That's the 4 principles of simple design. Make sure it works and keeps working. So always be running those tests after every change. Read the code. Ask other people to read the code. Is it easy to understand what that code is doing just by reading the code? And if it's not, maybe you need to introduce things with names that explain what that code is doing, whether it's constants or variables or methods or classes. There are all sorts of opportunities to embed that information. Look for comments in particular. Comments are a bit like user documentation. They're often an admission that the code is not self-explanatory. Look at the information in the comments. What story is it telling? And see if you can find a way to make the code itself tell that story. Then we look for duplication, remembering the rule of 3. Don't necessarily jump in too early. And removing duplication is a great way of more objectively discovering the kind of abstractions that we really need in the code. So often you will introduce things like parameterized methods and reusable classes as a result of removing duplication. Don't forget, after you've removed the duplication, reread the code. If it's made it harder to understand, if you've gone too far, then you need to revert that, which is why version control is so very, very important. Maybe there should be a 5th principle to simple design, which is that every design decision should be reversible easily. And then finally, is this really the simplest thing we could have done? Is there stuff in here that we don't need? Yagni. If you're driven by customer tests, bearing in mind that customers can be not just business customers, then you should have a suite of tests that is the ultimate arbiter of whether something was genuinely needed or not in terms of features, for example. And if all your tests are passing, but you can remove it or simplify it, then you should do that. So there you go, simple design. Good stuff. Easier said than done. If you try this out for yourself, I'm going to post a link to this code sample below. Easier said than done, but very easy to remember, hopefully.